Today's lesson is on section 3.4, solving equations with variables on both sides, or as you'll hear me sometimes abbreviate that on worksheets, I just say VOBs, just because I kind of an acronym there to shorten that up. But problems where there's variables on both sides of the equation. Sections 1, 2, and 3 in this chapter, we've been solving equations, and I've kind of listed out a set of steps that I want us to use when we're solving those types of equations. Those steps are still going to remain the same even in this section. There's just one part that we're going to focus on a little more now that we want to solve an equation that may have a variable on both sides of it. But otherwise, when they're going through the steps, or when you're going through the steps of solving problems, even in this section, I still want you to start out by distributing when possible. If there's somewhere to do that in the problem, that's the first step I want you to do, whether it be on one side, or have to do it twice, or whatever it may be. I want you to distribute when possible. Then I want you to still collect like terms when possible if you can do that on one of the two sides. But now on step 3, I've had you write these 3 steps down before, so you know what they look like. They should be in your notes. But the one part I haven't really focused on, or I've kind of glazed over up until this point, is this first line here on step 3. It says get the variable on one side and then use inverse operations to solve. Usually when we get to step 3, it's just usually that we're at a 2-step problem, so I can just use inverse operations. But I kind of have put that other step in step 3 also to say, okay, well, after we distribute and collect like terms, there is sometimes something else we have to check for. And in this particular section, that's where that arises. So I'm going to talk about those types of problems here, but I'm going to start off with an example like we've seen, just so maybe we understand and can kind of lead us into the first example and a problem in this section. But I'm going to start off with this example here first. 6x minus 20 equals 16. I want to remind us what will we do in solving a problem like this. Well, again, I could go through my steps and say, well, can I distribute? No, I can't in this problem. There's nowhere, no parentheses, no number in front of a parentheses, so nowhere to multiply some number times each of the terms. Is there anywhere to collect like terms on one of the sides? Well, on this side I have 6x minus 20. Those aren't like terms, so I can't collect them. 16 just by itself, no, I can't collect anything on the left side. So again, even today, I still want you to walk yourself through the steps when you're solving these problems. Again, I put these steps up because I think it'll get us to the answer in the simplest or cleanest, most straightforward way. Otherwise, if we do some problems out of order or some steps out of order, well, we can get to the answer, but sometimes we just run into some other kind of tricky areas. So that's why I advise you to use these steps. And even in problems today, start off with those first 2 steps. Distribute, collect like terms if you can. If you can't do either of those things, or once you've done both those things, again, now we get to step 3, but now today, we're going to concentrate more on this. Get the variable on one side. We don't have to do that in this particular problem, but again, what I want to remind us of is, okay, there are ways we can manipulate even things with variables, just like we can manipulate other numbers. At this point, the variable is on one side. X is all by itself on this side. But now I would use inverse operations. So 6x minus 20 equals 16. Well, at this point, to start getting the variable by itself, I would add 20 to both sides. Again, why do I do that? Well, right here, when it said minus 20 from the variable, I added 20 because that'll get rid of these from my problem. Negative 20 plus 20 is 0. So I can get rid of those constants on one side. That eliminates them from the left side and puts all the constants on the right side of the problem instead, and that's what I want. I would bring the 6x down, and I have 16 plus 20 would equal 36. But I guess the main part that I want us to remember is right here, how we can sometimes manipulate numbers. I can just subtract some numbers to get them away from one side or eliminate them from one side, and that will move them all to the other side then. So kind of keep that in mind as we go into the next problem. So here's the first example today that incorporates this section 3.4. And again, if you look at it, it looks a little different than the problems we've seen in the past. Directions say solve. Again, that means find out what x is. So we're going to have somehow get x by itself on one side and the answer on the other. Well, it says 32 plus 12x equals 16x. So you can notice right away, well, I have x's on both sides of the problem. That's how I know I'm dealing with a problem in this section, a VOBs problem, again, as I talked about it with. Variable on both sides of the problem. Okay. That's why I call these a VOBs problem. So how do we deal with these? Well, again, I'm telling you, and so I want you to feel familiar about this, is I'm not going to do anything different than those steps I started off with. Okay, so again, first refer to these 3 steps. Can I distribute anywhere in this particular problem? No, there's nowhere to distribute. Can I collect like terms on one of the sides of the equal sign? No, I can't do that. But now, again, we're going to concentrate more on this 3rd step. It says get the variable on one side. Well, again, I showed you this problem above. This problem right here to remind you how you can manipulate numbers sometimes. When I wanted to eliminate this 20, When I wanted to eliminate that negative 20 from this side, I just added 20 to both sides, and that got rid of it. Well, just remember that variables stand for numbers that we just don't know what they are yet. So it can make sense that I can also manipulate them in the same way I did on that problem above. If I have 32 plus 12x equals 16x, and what I'll tell people in class is to think about eliminating the variables all from one side, because that'll put them on the other, just like the problem above with the 20. That's what we're going to try to do. So what I'll think is, maybe how can I get rid of this 12x from this side? Because that'll eliminate it from that side, and that'll put all the x's on the other side. If I had no more x's on the left side here, then that means all the x's would have to be on the right. So how can I get rid of this 12x? Well, just like with the number up there, we had negative 20, so I added 20. Same kind of thing I can do on here. Since this says plus 12x, what I can actually do is I can subtract 12x. And again, I can do that to both sides of the equation because that's what keeps it balanced. Just like with constants, just like with numbers like we've done before. If I have 12x and then minus 12x, they essentially cancel out. Those give me 0 x's. And 0 of anything is just 0, so those are just gone from this side. Now all that's left is I have the 32 on this left side. On the right side, 16x minus 12x, just kind of like if you were collecting like terms on that side. If you had 16 minus 12x, 16x minus 12x, I just subtract the coefficients and keep the x with it. So 16 minus 12 gives me 4x. And then my last step, I can divide by 4 to both sides to get x by itself. X equals 8. Again, even in this problem, did we do too much new that we haven't been doing before in this chapter? No. I just kind of showed us one new idea, that I can move variables and manipulate terms with variables around just like I did with numbers before. But again, that should kind of make sense to us because variables just stand for numbers. So I should be able to do things with them just like I would do with other numbers. We'll look at another example here together. So this one says 8x minus 7 equals 4x plus 2. I'm thinking of problem number 2. It's example number 2. But it's 8x minus 7 plus 4x or equals 4x plus 17. I was trying to spit out that it was example number 2 too early. So example number 2, here it is. So again, when you're doing this problem, or any problem today, or as you go on, I still want you to think of those top 3 steps. Again, I've set up these 3 steps so you should be able to solve pretty much any equation that we run into. And especially this section 3.4, I'll tell you right now, it's one of the trickier sections we're going to go through, just because the problems have a few different steps. But I think if you can solve problems in this section, you can solve them in any section. So any type of equation that I could throw at you. But again, I still want you to walk through your steps. So number 1, okay, can we distribute? No, I can't. I don't have anywhere to do that. No, nothing with parentheses here. So I don't need to do that. Number 2, can I collect like terms somewhere? No, there's nowhere to collect like terms. So I don't have to worry about that. But step number 3, I'm going to look to get the variable on one side of the problem. Again, that's the new thing for today. So what's my first step here? Well, again, try to eliminate the x's from one of the sides, and that'll put them all on the other side. If I have 8x minus 7 equals 4x plus 17, what I'll try to tell students again is eliminate them from one side. In this problem, I'm going to choose to eliminate them from the right side here. And how can I get rid of that 4x? Well, I'll subtract it then, so minus 4x. Again, whatever I do to one side of the equation, I got to do it to the other. So on both sides, I have to subtract 4x. Again, why does it help me, or what we're talking about today, why does it help me to subtract 4x on this side? Because now 4x minus 4x eliminates these. So there's no more x's on the right side there. All that's left over there is 17. On the left side, 8x minus 4x now gives me 4x. I still have this minus 7 to bring down. And now, again, here's what I always try to do for students. And for anybody watching here, I try to set you up with a 2-step problem. Because once we get to a 2-step problem, or a 2-step equation, I feel pretty comfortable that we can solve it. And that's what we've done here by getting the variable on one side. Now I just have a 2-step equation that we've seen in 7th grade, 6th grade, maybe even a little before that. So we've seen a lot of these types of problems. So once we get to one of these, I feel pretty comfortable that we can solve it. This is 4x minus 7 equals 17. So now when I'm solving a 2-step problem, I'm going to add 7 to both sides, just like we've done many times before. Now I just have 4x on the left side. On the right side, I got 24. Divide both sides by 4. X equals 6. Just going to go through a few more examples here, again, just to make sure we got the idea of what we're doing. And also I'm going to recommend one more thing, and it will help out in this first problem here. One more thing to think about is what usually happens when we have an answer to an equation, and it ends up being like x equals 5 y equals 10 or whatever it may be. But just realize what's going on here. Well, we end up with the variable on one side of the problem. So there's the variable, and we end up with a constant on the other side. Okay, when I'm doing the solutions to any kind of equation. So when you're going through these steps, even that last step, getting the variable on one side, realize that to make this work, at some point you're going to have the variable on one side and a constant on the other. So like for example, in this first problem here, just kind of talking through something that I see sometimes students do, but I'll try to caution you away from this. In this first problem, sometimes students will say, okay, well, I can't do number 1, I can't do number 2, but number 3, get the variable on side. And they'll have the right idea that they want to eliminate the m's from one of the sides, but maybe they'll subtract 5m from this side and 5m from this side. Well, that'll get rid of all the m's over here, but then now what I've done is I've just put everything on the left side. 24 minus, well, 8m equals, and then sometimes people get confused, well, what's on the right side if there's nothing over there? Well, I guess you'd have 0 over here is what you'd have, okay? There's still a way to solve this. You could still add 8m to both sides and divide, and you can get the right answer, but I guess I'm just going to show in this problem what I would recommend doing, and one thing to keep an eye on is always think that I want to get the variables on one side and a constant on the other. So in this problem, here's 24. It's the only constant in my problem. It's on the left side. So let's think about trying to move the variables and get rid of this 3m so that I can get all the m's on the right side instead. Then I can be able to solve this. So at least it's an easier path to solve as opposed to the way I was just showing. 24 minus 3m. So how would I get rid of minus 3m from this side? I would add 3m. Okay, just like doing the opposite with other numbers, like we've done many times before. Okay, now just with a variable term. So if I add 3m to one side, I gotta do it to the other side. When I do it to the left side, again, it just gets rid of those. Negative 3m plus 3m, essentially those disappear. Okay, there's no more m's, so those are gone. The 24 comes down to the next line. 24 equals, 5m plus 3m gives me 8m. And now this last step, I can divide both sides by 8 to get m by itself. M equals 3. But just kind of one thing to realize with that problem, I wanted to showcase is that make sure you realize that at some point I have to have a number on one side and my variable on the other. So try to ensure that happens as you're solving the problem. One more example here we'll look at together. This problem right here says negative 20 plus c equals 4c plus 7. So if I'm going through my steps, and again I've kind of rigged them all up like this today, but we'll talk about more advanced ones tomorrow. But for today, I still would say go through your steps. I don't have to do step number 1 though. I can't distribute anywhere. I don't have to collect like terms on one of the sides. So now I'm just going to concentrate on getting the variable on one side, the new idea for today. Well, to do that, there's actually, maybe some people would see, there's like kind of 2 ways you could do this. And I've talked about this in class as well. Many times there's many more ways than just one to do a problem. I just suggest you go through this set of steps to help you. But there's definitely other ways you can solve it. I'm going to show in this problem that sometimes there are 2 different ways that you and your neighbor could do the problem, and it doesn't matter. You can both come to the same answer because in a linear equation there should just be one answer. So in this problem number 2, negative 20 plus c equals 4c plus 7. I'm going to start solving by getting all the c's on one side, getting the variable on one side, that is. So I'm going to start off, I'm going to try it this way. I'm going to subtract c from both sides. And that's like, if it helps you, you can think about subtracting 1c. There's no number in front, think of it like a 1. So it's kind of like minus 1c on both sides. That'll get rid of the c's over here. On this side, I just am left with negative 20. On the other side, 4c minus 1c equals 3c, and then plus 7. And again, once we've gotten to a 2-step problem, I feel pretty comfortable. And most students I think feel pretty comfortable with being able to solve something like this. Subtract 7 from both sides. I get negative 27 equals 3c. Divide by 3 on both sides, and I'm just going to bring my answer over here for a second. I get c equals negative 9. Okay. And again, that answer was good. That's the right answer. C equals negative 9. But maybe some people might have seen, though, in this problem, there is actually another way, an alternate way that I could do this problem. I'm going to erase the work that I had here. And again, remember, what are my steps telling? What does my third step tell me? Well, it just tells me that I have to get the variable on one side to start the problem off. Okay. Well, what if some people said, well, instead of subtracting c from both sides, I'll do this in a different color, but what if I subtracted 4c from both sides? Would that still serve the purpose that I want in step 3? Well, yeah, it still does, right? I'm still getting the variable on one side because I'm going to eliminate the 4c's from this side, so that should put all my c's on the other side. Well, what will happen then? Because this is a different way to do the problem. Well, I'm about to show you here. If you do this way, you'll find out something very interesting. If I subtract 4c from both sides, again, I'm still doing the same kind of thing that I was doing just a second ago with the other method that I did in red here. Okay, remember, here's my red answer. Keep track of that one. We got -9 for the answer. Well, now doing the problem in green. Subtract 4c from both sides. Again, it gets rid of the c's on this side. So now all that's left on this side is 7. On the other side, I have -20, and then c minus 4c would give me -3c. Okay. Now again, I've still gotten to a two-step problem, so I would want to solve it just by adding or subtracting something here, like adding this. This is -20, so I'm going to add 20 to both sides. When I add 20 to both sides, this -3c comes down, so -3c equals, well, 27. And divide both sides by -3, and what do you know? C equals -9, which is the exact same answer that I got the first time I did it. So one thing I tell students is don't worry, if you and a neighbor are doing the problem a little different way, that's not the worst thing in the world. You still should both get to the same answer when I'm solving these equations. Whether you want to clear the left side of the variable or the right side of the variable, doesn't matter. So again, as we see often in math, there's more than one way to do this problem. But either way, when we're doing linear equations, there's only one answer, so everybody should still be able to get the same answer no matter what route you take.